Right. Welcome everyone to the second day of the conference. We have the pleasure of having today Professor Giacomo Calzolari from the European University Institute. He joined the EUI 4 years ago from the University of Bologna, and he's currently professor in the Department of Economics of the EUI. Giacomo is also a research fellow at the Center for Economic Policy Research, and he has published in top international journals such as the American Economic Review, the Review of Financial Studies, and too many other journals to list here. His current research interests include competition policy, the economics of regulation and incentives, industrial organization, as well as banking regulation and supervision. And in his keynote, he will discuss today artificial intelligence, algorithmic recommendations, and competition. Giacomo, thank you so much for being here today. The floor is yours.
Thanks a lot. It's my pleasure. It's actually an honor to be here with you today. Let me just, okay, here we are. And what I would like to do in the next 45 minutes is to discuss a little bit about my recent research on artificial intelligence and impact on markets. As you can imagine, this is a very broad topic. So in a more humble way, I will tell you about my personal journey into this, what I think very important field and topic. So I'm not very keen on definitions, but I think it's useful that we have a common ground on a common understanding of what we mean for artificial intelligence. What you see here, it's my own definition, which is a patches of definitions here and there that I studied in these years. So the idea is to have software programs that often are combined into complex systems that use large amount of data to make predictions. And this may allow the automation of decision process into the realm of what would be normally the action of human intelligence. That's very broad definition. Why are we talking now about this, about artificial intelligence and its impact on markets? Well, starting from 2010, 11, we experienced a dramatic reduction of the cost of computation and the cost of data storage. This reduction in cost has revived quite significantly the possibility to use for actual market applications of algorithms, new algorithms, but also old algorithms that were developed in the 70s and the 80s. And this led to the first market application, real market application of artificial intelligence starting from 2012. So you see, we're 10 years ahead at this point. So as I'll show you, the market applications are quite significant and diffuse nowadays. Now, let me also cut the hype here a little bit. What artificial intelligence are we talking about here? So it's not fiction movie. It's not what is generally called artificial general intelligence, which is a multi-purpose version of artificial intelligence we don't have yet, which would be somehow surpassing human intelligence. I'm not talking about that. I'm going to talk about something very specific, market applications that are very specific and very effective though. So if you want currently, artificial intelligence is a general purpose technology like electricity. So we are talking about something very important that is going to have a tremendous impact on markets and on economies in general. So a general purpose technology is something that is pervasive. It's already the case. It's able to improve over time. It's one of the key elements of artificial intelligence, the element of self-learning and improve over time, and is spurring complementary innovation. So is an innovation that is helping to generate new innovations. Okay. So this is my definition of what is artificial intelligence, my understanding of why are we talking about it now, and what type of artificial intelligence is currently relevant for markets. There is a useful distinction that I'm gonna make and use in the rest of my presentation, and it's between expert systems and the modern artificial intelligence. It's important to make the distinction because, of course, algorithms are not a novelty in markets. There are industries where algorithms have been used, for example, in pricing. I will tell a few words on this. Since the 70s and the 80s, think about the airline industry or the hotel industry. They were using algorithms to allocate, to set the price of the products, to determine the occupancy of the rooms since several decades. Now, those type of algorithms were under this name of expert systems. The expert systems were developed in the 70s are quite complex type of algorithms that are built on two elements, a knowledge base and what is called an inference machine. So simplifying, the idea is that these algorithms are combinations, potentially very large combination of rules. If then, if the algorithms observe some realization of the state of the world, then you do this, okay? So this is the world of expert system. There were some market applications that they did not live up with the expectations, and somehow these generated what is known as one of the winters of artificial intelligence, where you had this somehow fading away of artificial intelligence from a market application. Now, as I said, from 2010. We started with a new type of artificial intelligence, the modern artificial intelligence, and where we go from rule-based, the idea of expert system, to data-driven approach. So these modern AI algorithms contain very few things. An objective, for example, the objective is to minimize some prediction error or to maximize some objective function. A description of the domain that the algorithm will monitor, will collect information from. And in some cases, I will show you an example, some exploration rules where the algorithm actively explores the environment in which it's deployed in order to get information, to obtain additional information. So if you combine this type of relatively simple approach with data, then you have that the algorithm itself learns what is the behavior that it should have and how to take decisions. So you see, we don't have coded if and then rules. It's the algorithm that learns out of observation and data its own behavior. And you can imagine that this is a quite significant development with respect to the expert systems. So here is a list of market applications. It's a long list, and I'm sure it's not complete. Search engines, recommendation system will be part of my talk today. Chatbots, or in general, advisors, robo-advisors, portfolio management, crime prediction of any type, filtering, like email filtering, self-driving cars, vocal assistants, automatic translation, analysis of legal contracts and clauses, and the writing of legal contracts, because now we have algorithms like GPT-3 of OpenAI that is able to write meaningful sentences. There is an entire debate whether these are really meaningful or just replicating what humans have said somewhere else. Pricing algorithms, this will be my other application today, supply chain management and all the medical applications and drug discovery that made. So you see, this is a gigantic list of applications, and you can imagine the impact that AI can have in our economies through these ramifications. Now, what are the implications for us, for economists, where, of course, as you can imagine, there are so many implications. I will not, of course, touch all of them. There is no way. I'm just referring a fantastic book that was written by a group of authors in 2019. It's published by NBR and is a research agenda for economists. And then MBR continues to have yearly a conference on artificial intelligence in September, which is, again, somehow exposing and presenting the most important and interesting developments for economists. Here is a list of our fields of research as economists that are certainly and quite significantly impacted by artificial intelligence. Everything that relates to production, R&D, innovation, growth, jobs inequality, and in general, the impact of AI on differences between workers, for example. The international dimension is quite important also. You may know that most of the patents on AI today come from China, and so you can imagine the type of geopolitics that is this will generate. Market functioning and organization, which is my own field as a microeconomist, and I'll tell you about what I've learned on this topic in a moment. Privacy, fairness, public policy for AI, and last but not least, how economists can use AI as a research tool. Because as I said, AI are tools for predictions, and we are eager to be able to see something to make predictions, of course. So how can we study? Here, I really entering into, in a very humble way, into what I've learned in the last 5-6 years. How can we study AI as economists? Well, there are different approaches here. I'm a theorist, and so my first attitude was okay, let's take an AI system, a realistic one, nail it down and see how it works. What will be the implication in actual market applications? No way to do this because AI systems are complex systems that have dynamic implications, and there is no way you can represent in closed form these objects. So it's a dead end. Then you can try to do some empirical analysis. There are some papers taking this approach, of course, but there is a lack of good data, in particular because there are very large companies nowadays using AI and they have proprietary data. And so access to this data is to some extent limited. And a third approach would be, and this is the one I follow with the group of co-authors, is to experiment. So let me be more precise on this. An experimental, or if you want, simulation approach is the following. We take actual AI system. What I mean with actual, we really mean state-of-the-art AI systems that are used for certain applications. And we plunge them into a synthetic and controlled economic environment. Synthetic means that we generate explicitly and directly any key economic dimension of the economic environment. And control means that we can control the data that the algorithm is using in order to learn and to take decisions. So if you take this experimental approach, there are some challenges, at least two. One is that the algorithms that you are using for your specific application must be sufficiently close, if not exactly what you would observe in actual market application in the real world. The second challenge is that economic environment that we design must be sufficiently realistic. And on this side, I would say that with some experience, we know as economists that how to properly design a market, and this is the approach that we have taken. So the intended contribution of this approach is twofold. On one hand is a methodological approach, bridging economic analysis and computer science. So somehow making what computer scientists do close to our economic models and having the two fields actually using the same tools. And the second contribution is to provide specific implication and analysis on specific applications. So the plan of what I want to tell you next is the following. I will discuss two market applications that have been studied in the last, let's say, 5 years. One is AI, artificial intelligence for pricing decision, and another is AI for recommendations. So the plan for each one of these two topics is I will show you the specific application. I will introduce the precise AI algorithm that we have used for this application, a few words on the analysis and the results, and our policy implications. So if you see, this is a modular approach that we used by means of this experimental approach for two different environments or issues, pricing and recommendation. And this, as I said, is a long journey that I've taken with my co-authors, Emilio Calvano, Vincenzo De Nicolò, and Sergio Pastorelli. So let's start. AI for pricing. Now, algorithms used for pricing are already populating our markets. Firms are increasingly using pricing algorithms to delegate the pricing decision to these automated systems. Just to give you an example, if you look at Amazon Marketplace, already close to 10 years ago, so the figures have certainly increased, 1/3 of the prices that you were seeing as buyer on Amazon Marketplace was set by an algorithm. And if you think about financial markets, again, the use of algorithm is widespread. Amazon itself somehow emphasized the fact that if you are a seller and you use a pricing algorithm, you may increase efficiency and profit, by the way, and their profit, by the way. And so, and it's also interesting to see that there is an entire repricing industry, an industry of software companies that design algorithms specifically for pricing applications. So here is an example. It's really turnkey services for very little money. You pay $45 and you have access to a tool that is completely integrated, for example, into Amazon Marketplace and does the repricing, the pricing of your good as a seller automatically. Okay? And also there are large companies, like this is an example of Shell, the oil company that is using pricing algorithms to set the price at the pump station. Now, what is new? Well, as I said before, pricing algorithms are not a novelty. Since the 70s, the 80s, some industries were using algorithms. The novelty is there that we are currently going from an environment from type of algorithms that are in the class of expert systems, this elaborate collection of if-then rules, into the modern AI algorithms, where you, as I said, in a sense, are simpler objects because they are the programmer just specified objective function. For pricing application, the objective function typically is the profit of your firm as a seller, which data to monitor, to use, to collect from the environment, which is now a market in this precise application, and how to learn through experience and through observation. So let me tell you how we developed this type of analysis. We consider a very simple economic environment where firms delegate their pricing decisions to algorithms. So you can see the seller or a firm delegating the pricing decision to an algorithm. They are selling differentiated products with some demand function. Prices are perfectly observable. This is another property of digital markets. Prices are typically observable and algorithms can feed in this information systematically. And each AI pricing agent repeatedly sets the price of the products over time. Okay, so PIT is the price that algorithm I, that is the algorithm of firm I, is setting at time T for its product. And the aim, this is written in the code, is to maximize some expected discounted sum of the firm's profit, as you see here. So the research question is, imagine an environment, an economic environment that is populated by pricing agents of this type. I will specify more what I mean with that. And the question is, what prices will these AI-powered pricing algorithms will end up with? Now, before we go there, I have to clarify what type of AI we were using for this type of exercise. Okay? As I said before, the challenge of this experimental approach, one of the challenge is to use a realistic version of the AI algorithm. Now, the type of algorithm that we used, and I'll come back on the justification, let me first explain what type of algorithms we have used for this type of research, is called reinforcement learning or Q-learning algorithm. These are algorithms that essentially do two things. When they decide a price at any point in time, they take a first decision. The first decision is whether to exploit, this is the computer science jargon, whether to exploit the market, which means setting in the period a price which, according to the information that the algorithm has, is profit maximizing. The alternative is for the algorithm to choose a price that is an explorative price. So it's an exploration, suboptimal price chosen according to some distribution. It could be simply uniform distribution. Then the second thing that the algorithm does is observing the outcome of this decision and learn through experience. So what you see here is what is called a very simple pseudo code of this type of algorithm. The information of what is the value of using a given price PT in a given state of the world S is summarized into this object, which is the Q function. That's the reason of the name Q-learning algorithm, is stored into this object. If you have discrete action, this object is just a matrix, or could be more elaborate things. This is where you store, the algorithm stores the information. The quality, that's why they are using the Q, the quality, the value of using a given price in a given state of the world. So as I said, with a given probability, the algorithm decides to choose the greedy price, which is profit maximizing, and with complementary probability will instead explore randomly choosing a price. Then at the end of each period, the algorithm will observe the profit that the firm has obtained at the end of the period, given its own price and the price of the other sellers, and will end up in a new state. Imagine there are just two algorithms. The new state is simply the prices that the two algorithms have used in the current period. And then there is the learning phase, which is an updating of this Q function according to this formula here, which is simply a linear convex combination of what the algorithm knew before, QT, and what the algorithm has learned through experience, the profit and the new state of the world, which allows the algorithm to foresee what will be the best action for tomorrow. This is Q-learning. Why we use Q-learning? That's the motivation. It's a very simple algorithm. It's domain-free. You don't need to specify anything about the market structure, demand function. The algorithm is able to learn autonomously. It's not fancy. There are very few hyperparameters, as you may have seen. There is this hyperparameter alpha, which is the convex combination, is the learning rate, the parameter that controls the exploration rate, and that's it. It works. It's known that with a single agent, this type of algorithm is able to identify the optimal policy in this dynamic environment. It's popular and is effective also in games. By the way, Q-learning is the core engine of the algorithm that a few years ago was able to win against the world player in the game of Go, which is one of the most complicated games that we have, and more recently also to win over chess. another very complicated thing. So let me go to the results now. What you see here is the price distribution of our economic environment that we have populated with algorithms of the Q-learning type. We let them learn sufficient amount of time, and this is the price distribution that you would observe after some learning. Now, what I've indicated here is what would be the competitive price, and the arrow here shows you the monopolist price, as if the algorithms were behaving as a single firm in a, let's say, cooperative or collusive agreement. So a first observation is that on average, the prices that these algorithms have learned to set autonomously is very high, is very skewed towards monopolist pricing and far away from perfect competition or competition. Now, the question is, what happened? Because two things can happen here. The first thing is that this algorithm didn't understand the economic environment. They didn't learn what the environment in which they were operating, and more precisely, with the eyes of industrial organization, they didn't learn that the best thing to do if you find someone charging such a high price is to undercut by an epsilon or whatever. You get most of the demand and huge profits. That's one possibility. They didn't learn this thing. They didn't learn economics. The other possibility is that they learned something else. So then we decided to open up these Q-learning algorithms and look into the algorithms and see what they've learned. And this is an attempt to do. The problem is that these algorithms are very complicated objects. Even though you see the application is simple, few algorithms, they're very complicated objects. It's really difficult to open up these boxes and look inside. This is a known problem in computer science, and they are developing tools that are called explainable artificial intelligence, constraining artificial intelligence tools in order to be understandable by humans. This is not understandable. This is one way to represent algorithms, and we work with this, but we were not able to understand. Then what we did is something much simpler. And this is where somehow we were happy to use our background as a theoretical economist. We provoked the algorithms. So the exercise that we did is the following. This is an example where we are considering just two algorithms. We let the algorithms learn, and this is what you see they learn in this particular example. They learn to set very high prices. On the vertical scale, you have the prices. The green line here is the monopolist, perfectly collusive price. On the orange line will be the competitive price. You see, this is consistent with the price distribution I was showing you before, very high prices. Then we provoke the algorithm. What we did is the following exercise. We took the red algorithm and we forced it for one period and one period only to drop the price by some amount. Okay, so this reduction that you see here is imposed by us. Then we released the two algorithms free to do what they wanted to do, according to what they have learned. And this was the discovery. The blue algorithm reacts to the price cut of the red algorithm with a dramatic price cut. Then they stay at low prices for a few periods, and then they go back at high prices. So what they have learned is three things, very sophisticated things. Reward, if you charge high price, I charge high price as well. Punishment, if you drop your price, I punish you. The blue algorithm is punishing the deviation of the red algorithm. And then I forgive you at some point. Why forgiveness? Because they're learning in the stochastic environment. And if you don't forgive someone in stochastic environment, you're doomed. The green trigger strategy, I punish you forever, is completely stupid strategy in a stochastic environment. You must learn forgiveness. So this was our discovery in this application. Now, it's also interesting to see how is profitable our deviation, the deviation that we force the red algorithm to use. Well, of course, you see, these are profits, no more prices. These are profits of the two firms. You see that the first period when we impose the deviation, the red algorithm makes a lot of profit because it takes the blue algorithm by surprise. But then it comes the punishment of the blue algorithm. And then you see that the profit of the red one goes down for quite a bit of time. And if you calculate the integral of plus and minuses, the sum is always negative. So they have learned to collude tacitly with no communication in an incentive compatible way. Okay? That was for us quite a discovery. And it's a robust result. We did many different extensions. And here, I think it's useful to spend a few words on the flexibility of the experimental approach, because it seems we can control everything. We can do a lot of comparative studies in this environment. I was showing you the case of two firms. We did it with many more firms. It's consistent with theory. The more the firm, the lower the equilibrium price. Differentiation, asymmetry, uncertainty, entry and exit, inventories, whatever, the result is still there. They learn this incentive compatible pricing strategy. We complexify the environment, more prices, longer memory, changing the hyperparameter, learning entrant. That was interesting. Imagine an environment with our two algorithms which have learned what I've shown you. Now imagine a maverick entering the market that has to learn how to behave. What happens? Would the new algorithm take advantage of the algorithm already in the market, or is what happened? It learns to behave as the colluding algorithms. Okay, so it's a robust result. It's simulation, it's not real market. That's the limitation, of course. There are new emerging empirical evidence on something very similar happening in the gasoline price. There is a paper by Assad and others in Germany, where they were able to identify a company that started to use precisely the Q-learning algorithm that we're using, and they have some convincing evidence that something similar happens. Now, let me conclude on this example with a few comments on policy, in particular on competition policy. Let me remind you one important thing. What, as economists, we think is collusion, passive collusion, that is a reward punishment scheme leading to high prices, as exactly the one I showed you before, is different from what authorities, competition authorities, use in terms of administering competition authority for collusion. There must be this mutual understanding. And the second element, there must be evidentiary standards, hard evidence, in order to prove that there was an intention to agree. Now think about the algorithms. They don't talk. They don't have intention unless you want to enter into this philosophical discussion of whether these are sentient beings. So currently, our competition policy is unable to deal with self-learning colluding algorithms. So this is really an interesting interdisciplinary environment where we need economists, we need computer scientists, and we need lawyers, legal scholars, in order to understand what to do. And certainly we have to change the policy, for sure. Second example of the approach I wanted to discuss with you today is on recommendation systems. I'm sure that you have experienced this feeling. You go online, you want to buy something, and you discover that there are so many options for you available that you don't know how to search what to buy. And this goes to products. It's relevant for news to read, movies, songs, assets to buy, financial assets, papers to read as academics. So how do we do with this ocean of options? Just few numbers. In Amazon Marketplace, you have 300 millions of products that you can buy, several millions of songs to listen. The Netflix catalog is several thousands, and they keep changing the catalog frequently. 26 billions of videos on YouTube. We can question the quality of those videos, but they're still there. There are too many alternatives to know the existence of these alternatives. Yeah, so even if you know your own preferences, you don't know whether there is a product that is close to your preference and relevant for you. So we need some help in this ocean. We need a sextant to navigate. And this is the recommender system. Recommender systems are, again, software programs, AI software programs that provide personalized recommendation or suggestions to users about specific items. Again, notice it's a prediction problem. Before it was a problem of predicting what was the optimal price for the firm. Here is predicting what is the optimal product to recommend to a consumer, to a user. Okay, so this just examples. This is the Amazon recommendation system in place, how to rob a bank. I don't know why my author is using this slide. Maybe unhappy with salary. And these are the recommendations of Spotify. This is the recommendation matrix of Netflix, divided by different genres of the movies. And these are other applications, products, music, movies, videos, socials, apps, financial products, which assets you want to buy, what are the most relevant and best fit for given your conditions in terms of assets, academic articles to read. And if you are an editor of an international journal, now there are systems that provide recommendations on reviewers, which is one of the most complicated tasks for editors. A few years ago, these recommendation systems were a total disaster, completely useless. Nowadays, they are improving much more and they're providing good recommendations. I'm not saying that I'm using it systematically, but it's useful. Now, why do we care? We care because these systems are already deployed in market and they are already shaping our choices. You look at these figures, I think they are astonishing. 75% of the movies on Netflix that we watched movies are recommended movies. 35% of items that are viewed on Amazon are recommended. 40% of the song on Spotify, and 60% of the videos on YouTube are recommended videos. There are some worries about the implication of algorithmic recommendation. There is a hot policy debate because there is a risk of competition given this. We don't know exactly. So consumers are exposed to this recommendation and they choose accordingly. And this is shaping markets. Think about financial markets, for example. And there is also a risk in terms of democracy, because if you apply this to news, then it's quite easy to imagine manipulation of how we view very important topics like politics. So there are authorities who already started to think about how to regulate these algorithms. There is a general issue that we'll focus on more, which is the rich get richer effect, the fact that the recommender system may exasperate popularity. I'll show you in a moment. Essentially, the idea of the recommender system is to use information that they observe and transform it to a recommendation. And there is a risk of a feedback loop between the information that the recommender system observes, the recommendation that it makes, and the fact that the recommendations, once they're used by users, are generating the new data that the recommender system is using to make new recommendations. This feedback loop. Actually, we would say there is a problem of endogeneity here. and it's a general issue of artificial intelligence. Let me pause a second here. I think it's a very interesting topic for economists. Artificial intelligence are self-learning algorithms that use data. But once you deploy into the market, these data are becoming the new data the algorithm using to self-learn again. So there is a circle here, and we know that endogeneity generally creates some problems, certainly for econometrics and our approaches. So let me give you a conceptual, very simple conceptual framework of how a recommender system works. You should imagine a very large matrix. This is a toy example where you have in the rows the users, in the columns the possible items. Think about Amazon, millions of users, millions of items, so a gigantic matrix. And the entry of this matrix is the rating. The numbers that you see here are the ratings that were reported by some users who has used that particular item. So user one liked, I tried, experienced item B and C, and liked that item B more than C. There are two features of this rating matrix, which is the core, the source of data of a recommender system. The first feature I already told you, gigantic, millions of items and users. And the second item is that they are very sparse, or the density, the non-empty cells that you would find in this rating matrix in reality is very small. From 1% to 2% of the cells are non-empty. So we have recommendation for very few relatively to the large matrix items and users. So the idea is to take this type of data and transform it into predictions. So we did this with this experimental approach that I was mentioning before. We took state-of-the-art recommender system, which is called model-based collaborative filtering. I will not enter too much into the details, but it's, again, relatively simple. It's an algorithm that does the following thing. Step one, it assumes some model for the preferences of the items based on a very simple latent factor models, K factors. So imagine that you can describe each consumer according to some proclivity towards these factors, and each item has a vector of intensity of each of these factors. Then you have a description of consumers, you have a description of items, and the algorithm combines it in a vector product, as you see here, the summation. If you want to have some idea of these items and how this is built, think about proclivity of user H towards of user I towards factor H as how much you like sugar. Okay, this is your proclivity to sugar. And on the side of the product, the intensity would be the intensity of sugar present in that particular item. Okay, sugar is one dimension, one of the factors. You may think about different factors and you put together as a set. Step two, once you have this model, you estimate this theta and beta, the characteristic of all the users and the characteristic of all the products. When you have these vectors, theta and beta, things are very simple because by, again, product vector, you can back up the rating of all users and all items, even if they never tried those items. And then you order these calculated ratings, and then you make a recommendation according to the order. Okay? Or you recommend the best product according to the prediction, or the best, I don't know, 10 products. Let me skip the literature. The approach is the same as I was saying before. We plunge this algorithm in a economic environment where there is a platform using the recommender system. There are users, consumers, and there are sellers of these products or these items. And we control preferences. That's one of the benefits of this experimental approach. We control items, we build items, we build users, and we throw them into this market where there are these recommendations. So let me skip in the interest of time this thing here. I want to emphasize a little bit more about the data generation. So where this data come from? We did two versions. In the first version, the rating matrix is generated by exogenous data that we randomly draw from population of items and users, so that we were sure to be able to mute the feedback loop effect, the endogeneity issue I was discussing before. And hence, we also have a version where instead, the data that you would find in the rating matrix is generated period after period through the recommendation and the decision of the users. So that in the end, by means of this differential approach, we can say whether what we observe is generated by the characteristics of the algorithms or by the characteristics of the endogeneity of the data. We need a benchmark for this analysis. We need a benchmark to compare what happens with the recommendation system with respect to a world in which we don't have a recommendation system. So we describe this world where we don't have a recommendation system as a standard model of search, consumer search. There is a population of products, you randomly search at some cost, and then you go on and on searching till the point where the expected gain of search is smaller than the search cost. Then you stop and decide how much to buy. So I want to use last few minutes to show you two types of results. One result is on market concentration, comparing market concentration in terms of market share for the different products that we have with the recommender system with respect to what would happen if you don't have a recommender system deployed in this market. What you see here is one typical measure of market concentration that we use in IO, but of course in other environments, the Irschen-Erfindal index. The scale is from 0 to 10,000, which is typical scale used in competition policy. If you look at individual search and the case of recommender system, you see that the recommender system, they do increase market concentration. The different alphas, alpha 0, alpha 1.5, and 1, refer to different level of product differentiation. With alpha 0, products are horizontally differentiated. Alpha 1, they are vertically differentiated, meaning that there is one product out there in the market which is, in terms of vertical quality, the best product available. Of course, the problem is that the consumers do not know which one of these products, which is this product, sorry. And you see that no matter what with the product differentiation, recommender systems do increase market concentration. And the bottom line is the recommender system with endogenous data. The first was the recommender system without endogenous data. So you see that endogenous data, they do further increase this market concentration. So summarizing, the recommender system generates what you can call a superstar effect, enhancing market share of some popular items. And there is a feedback loop present here. Again, if you want to interpret this type of result, you have two options. One possibility is that what's happening here, that's for some reason, lucky few firms get recommended and more, and somehow they enter into an entrenched position of where they can exercise monopoly power. Or we know that high market concentration can be also associated with very competitive markets, right? Where small differences in terms of prices generate huge consequences in terms of market share. So what we did, we built on this a model of equilibrium prices. And it's simple to do because the recommendation system, they simply generate a form of demand function. Consumers are expressing their behavior through the mediation of the recommender system. Okay? So we again compare the case of recommender system with exogenous and endogenous data against the benchmark where there is no recommender system, and we study Nash equilibrium prices in this market. This is what happens. Irrespective of product differentiation, the three columns, you would observe that the price is much lower with the recommender system rather than with the individual search. So recommender systems are increasing market concentration, but at the same time, they are intensifying competition. Now that firms know that there will be the recommender system mediating the decision of the consumer, they're forced to compete harshly and reduce their prices. So there is a strong pro-competitive effect of recommender system, which is robust. It's still there, even if you consider the feedback loop, which is somehow increasing a little bit in prices, but prices are still lower than the case of no recommender system. The intuition, I will skip, but the idea, we discovered that the idea is that the recommender system is reducing heterogeneity in the evaluation of the consumers, which generates a counterclockwise rotation of the demand function of our consumers, which means that consumers are more elastic, so the equilibrium prices must be lower. So then we also studied a situation where the recommendations were biased. You may know that platforms using a recommender system, they manipulate the recommendation in order to profit more, for example, for products, for recommended products on which they're earning larger rents or profits. Okay, so that's a very topical issue in terms of policy. We are studying also this case, but we still observe this fact. So last word on the policy implication, and then Claudio, I'm done. Last words on the policy implications of this recommender system. First, we observed with this experimental approach, we observed that recommender systems do increase market concentration. This is source of worry. We also saw at the same time that the increased competition and the outcome on prices is reduction of prices, which is a good thing in terms of market efficiency, and if you just use the standard of consumer service. Certainly a good thing in the short run. The implications of the long run are less obvious, because more intense competition, lower prices. If you have a somehow fixed cost as a seller to be active seller in the market and the competition intensifies very much, you may be forced out after some time out of the market. This may end up with the reduction of the variety of the products that are available. So what are the policy implications out of that? Frankly, this is too early for me. The previous research I was mentioning before on price competition, we had some time to elaborate, to think, to interact with legal scholars, and we have some proposals that we put forward in a short paper on science on policy tools we could use to to deal with the price competition. For the recommender systems is frankly too early. We just discovering these things, these results I was mentioning right now. Certainly, transparency and an access to algorithms, the possibility to audit the algorithm that these large platforms are using for recommendation would be a necessity. I mean, it's not something very, very clever here to say. You may know that the European Commission has drafted a directive on artificial intelligence that is precisely containing some remarks in this direction in terms of transparency and access to algorithms and to data as well. Computer scientists are aware to some of these problems of recommender systems, and they are trying to design constraints in what they call personalized artificial intelligence. There is, interestingly, an entire branch of artificial intelligence that they call personalized artificial intelligence, that is tools in machine learning that are precisely designed to deal with single individuals, and are using some constraints in these type of algorithms in order to cope with some of the issues I was mentioned before. And at the moment, my suggestion in terms of policy is potentially regulation is important because you saw the market implications are huge, but I would handle with care at the moment because we know too little and it's probably too early. And that's all. Thanks a lot for your attention.
Thank you very much, Giacomo, for this keynote and for minutes, which somebody is actually concerning an EUI policy reference. Let's see whether there are any questions. Please.
Yeah, thank you for the amazing talk. I was interested in the pricing side of things. So my question is, why don't they adopt it with the algorithm? Right? The topic actually well, because they have to appear as if they're not, perfectly colluding. So it seems to me that what's driving value thoughts is this randomization that you attach to the part of the algorithm. Right? And so I was thinking, what if you put a bug in it? You put another agent, right, downward, will always do Nash, right? What do they have to do? They have just to, go back to Nash, then they randomize, but then the players just downward will stay at Nash. That will be the regulator. What will happen is either they stay at Nash or they go out. Me, that's how I see it unfolding. Right? So this is how we see the policy intervention in such a situation. I want to tell
Yeah, that's an excellent point. So let me answer this way. Imagine you are a developer of an algorithm, pricing algorithms, and you have a client that comes to you and tells you, look, I want a new algorithm for my pricing decision. And you say, I have a clever idea. There are algorithms out there in the market making a lot of profits. Let's be smarter than them and go in the market with an algorithm that undercuts them systematically. Okay, you deploy this algorithm in the market and you discover that the price goes down. Your client would not be very happy, right? So, so the industry, you cannot hope for out of the industry something like this response. Now, what you just said in terms of market intervention, market regulation, it's certainly very powerful, but is very unlikely to happen because it's price regulation. And I would say, luckily enough, we don't have price regulation except some special cases, some special environments. So both these two solutions are complicated and not applicable in most of the markets.
But you see that, as you pointed out, there is a lot of intentionality, right? It's not that there's some machine that is just making up things. No, there's a folder, you program it, right? So there's an intention. It's very moral, right? It's just not.
No, sorry. I disagree. We discuss a lot with legal scholars about this intentionality, which is the cornerstone of competition policy, actual competition policy in the real world. There is no intentionality. The element of the algorithm that I coded is, this is your objective, my profit function. I want you to maximize my profit function. I think we all agree that this is the objective of a serious entrepreneur. Second instruction, explore the market, and that's it. There is no intentionality. It's the algorithm that autonomously learns the behavior. And all the theater that are added there, forgiveness, punishment, etc., it's just us trying to give a sense of what I showed to you. There is nothing intentional. It's simply, it's not so simple, a system that has embedded for some reasons, and this is something that we're studying now, why this system has embedded this attitude to learn this type of behavior. But I humbly disagree. There is nothing intentional here, and that's a problem. There's a question there. Sure.
Thank you so much, Giacomo. Less of a question, more appreciation. So, I think I understand what you mean. I think there's no question about it. But regarding the possibility to monitor and actually compute this from policy, that is more about do the firms that are using these algorithms understand that they will implement tacit collusion? And is it then tacit still if you want to understand, or even just like this general results that you presented to us? So at which point you penalize collusion, whether it's tacit or whether it's implemented by?
I completely agree with you. That requires a change in paradigm in competition law altogether. There's another question there.
Thank you very much for the impressive talk. I thought you showed a very impressive point that the algorithm measures that operation strategies like Fit for That is more efficient in terms of profit than playing with. This is something that aligns to our model, but we can't, I guess, replicate with the same result in experimental setting with humans because they don't, conform so much with the model. But do you think that even more and more decision power will be placed on that algorithm, our rational choice model, like come closer and closer, at least on the production side, to like the theory realize finally?
That's another very interesting question. I agree. So I have one of my co-authors, I will not tell you who, makes this claim. These algorithms are the rational players we were looking for ages to use in the lab. Let's get rid of biased students from our experimental lab and use this type of machines in order to have the real rational player. It's a bit it's kind of extreme, but there is some truth in here, I think. Certainly they don't have biases. They're not coded unless you add as a coder some bias, as in the example I was mentioned before for the recommendation systems. It's interesting, we did some comparison in the case of the pricing algorithms with what we observed in the experimental lab for cooperation or collusion. And they do much better than humans in the ability to generate cooperation. If you look at the experimental literature with humans, above 3 players, with 3 players, they more or less are still able to implement some collusive agreements or cooperation, but above 3, they end up competing. In some cases, even more than we would expect with perfect competition. So, and on the other hand, with algorithms, we went up to 10 algorithms. As I said, the profitability reduces with the number of algorithms, but you still have quite a bit of cooperation, much more than what you would observe in experimental labs. Yeah, there's a question there.